Let's start this lesson off with an example. Suppose you sell hats, and your net earnings as a function of the number of hats you sell in a year is given by f of x equals 12x minus 5,000. So x is the number of hats you sell, and f of x, the output, is your net earnings. Also, suppose your net profit after tax is given by g of x equals 0.75x, where x is your net earnings before tax, and then g of x, the output of that function, would be your net profit after tax. Question 1. Determine your net earnings and net profit in a year where you sell 10,000 hats. So my net earnings is given by f of x. So I could quite simply say, well, x here in f of x, x represents the number of hats, so f of 10,000 equals 12 times 10,000 minus 5,000. So I would have 12 with 4 zeros, 120,000 minus 5,000. So $115,000 would be my net earnings. And then g of x gives me my net profit after tax. So I would say g of my net earnings is 0.75 times my net earnings. 0.75 times 115,000, and I would get $86,250, and that would be my net profit after tax. And then we get question number 2. Determine a single function h that gives the net profit after tax directly from the number of hats sold. Now, think about what's going on here. We start with the number of hats, and then from the number of hats, we get the net earnings. And then from the net earnings, we take that and calculate the net profit after tax. So we're basically going number of hats to net earnings before tax, and then we're going from there to the net profit after tax. Okay, and we have a function that takes us from the number of hats to the net earnings, right? We're told what the relationship is. It's 12x minus 5,000. And we're also told what the function is to go from net earnings to net profit. It's 0.75 times the net earnings. Okay, and in both cases, the x, because the argument here is x, this x refers to the input. And because the argument here is x, this x refers to the input of this second function. So what we really have is an input, number of hats, into some function f. It gives an output, and then that output immediately goes into another function g, and it gives an output, right? Here in the middle, nothing happens. It's the net earnings. The net earnings is the output of one function, and then it's the input of the other. Now, one way to represent this is we say, look, we want to go, f of x, so the number of hats, and then computed. Now this whole thing is this output here, which becomes the input for the next machine. So we have f of x is itself an input of g. G of f of x. The way we say that is g of f of x. Okay. Now there's another notation for this. G of f of x. Okay, these are identical. And there's another notation. We can also say g of f of x, like that. Okay, so these are three different ways to say that we're taking our input number of hats, we're using the f function, and then we're taking that output and using it as the input to the g function. Okay, and now algebraically, we're asked here for a single function h that does that. That gives the net profit way over here when the input is the number of hats. So in other words, h of x in our example is g of f of x, or g of f of x. And so to evaluate this, we need to first figure out, well, for some x, what is f of x? Well, we already know it's 12x minus 5,000. So this part here, if we're using a variable of x to represent the number of hats, becomes 12x minus 5,000. So what we now have is g of 12x minus 5,000. But g of 12x minus 5,000, we're now inputting an expression, and that's okay. When we input an expression to g, the function g was 0.75 times the input. Well, the input happens to be an expression, and that's just fine. So we have 0.75 times this expression, which of course we can simplify using the distributive property. This is 9x minus, what would that be there? I guess that would be 3,750. Okay, so h of x is this. And now if we go and we take our original example where we had 10,000 hats and we substitute that into h, we get 9 times 10,000 minus 3,750. That's 90,000 minus 3,750. And that is exactly what we had before, $86,250 net profit after tax. Okay, so H in a sense is a bigger machine that sits right here, and inside this big machine H, we have F and G. And you put your number of hats in as an input to H, and then inside you don't see what's happening, and you just get the output of the net profit after tax. But what's actually happening inside is H is getting F to give an output, and then taking that output and putting it into G, and getting the output of G. Here's a little metaphor of what's going on. You know, if you have a long, rough piece of lumber, you might take it to a miter saw, M of X. It takes in long pieces of lumber, and it outputs shorter pieces of lumber. Okay, still rough, but shorter. And then you take this shorter piece of lumber, and you put it in a jointer. What does a jointer do? Well, it takes a rough piece of lumber, and it makes it smooth on one side. And actually, we can put it through the jointer twice to make it smooth on two sides. So then, instead of being rough everywhere, it's smooth here and it's smooth here, and the jointer will make sure that this is a perfect 90-degree angle. Then what do you do with that? Well, then you would normally go over to a planer. That's another machine. When you put in a piece of lumber that's rough on two sides and smooth on the other two from a jointer into a planer, you end up getting it smooth on three sides. You only have one side left that's rough. Then what do? Well, you go over to a table saw. The input from the table saw, then on the output, you end up with a board that's the length you want, and it's smooth on all four sides. Okay, if you wanted to take this process and represent it algebraically, you would say, look, the first thing you do with your lumber is you put it through the miter saw. Then you take that output and you put it through the jointer. And then you take that output and you put it through the planer. And then you take that output. I'm just pausing because actually, I guess technically you go through the jointer twice. Let's just keep it simple. Okay. Then you go through the planer. Then you take that output and you go through the table saw. And then your final output here is a smooth piece of lumber. Now, what you're going to need to be able to do is get very, very comfortable with function notation and compositions of functions. So let's suppose we have a few functions here to work with. So here we have them, three functions. F of x equals 3x minus 5. So whatever the input is, we times by 3, subtract 5. G of x is x squared plus 2x minus 1. So whatever the input is, we square it. We add that to 2 times it, and we subtract 1. And h of x is kind of a funny machine. H of x equals negative 3. That means no matter what the input is, it's going to give out a negative 3. Okay? So that's an interesting machine right there. Or interesting, actually in some ways it's not interesting. But it's different from the others because you can see x isn't over here, so the input actually has no bearing on what it gives you. Okay? So now, let's take a look at f of g of x. What is that? Pause the video here and see if you can do it. Okay, so this says I'm going to apply this function, and the argument of f is the output of g, which is this whole function. Okay? I mean, the output of g when the input is x is this here. So I'm getting 3 times the input of the function to f. The input to the function f is g of x. So I have 3 times x squared plus 2x minus 1 minus 5. That's f of g of x. And now I could do a little bit of distributive property. I could collect my two constant terms there. And that's what f of g of x is. Now, what if it said f of g of 2a? What's the difference? Well, the only difference here is that our input to g is not just x anymore. So we're going to have to actually take this input and input it to g. Remember, g of x, I'll put it over on the side here. G of x is x squared plus 2x minus 1. F of x is 3x minus 5. So this time, I have 2a as the input to g. So in this g function, I have a 2a squared plus a 2 times 2a minus a 1. That's g of 2a. But this output is the input to f. So now this is what's going to have to be multiplied by 3 and then 5 subtracted from it. So 3 times this whole thing minus 5. That's 3 onto 4a squared plus 4a minus 1 minus 5. Or in other words, 12a squared plus 12a minus 3 minus 5, or 12a squared plus 12a minus 8. Okay. What about, we had f of g of x, what about g of f of x? Does that change anything? Does changing the order here change the result? And the answer, if you just think about the metaphor with well, if you know woodworking, if you think of the metaphor with the shop tools, it does change something. If you take, let's cut it on the miter saw first, so you have a shorter length, but you have this rough wood. If you take the rough wood and you run it on your table saw, sure, you'll clean up one side, but you're not going to clean it up very straight, because the wood that's running against the guide, if this is a rough piece of wood, it's rough everywhere, as it goes against the guide here on the table saw, yeah, it'll clean this, but it might not clean it in a straight fashion, because this isn't going to be nicely smooth against the guide. And then when you take that and you move it over to the jointer, all sorts of problems could happen. So yeah, if you do things in a different order, you'll get a different result. Let's remind ourselves, g of x is, what is g of x again? It's x squared plus 2x minus 1, I believe. And f of x is 3x minus 5. So what's going on here? Well, our input to f is x. If you're inputting x, you get exactly this. So my output of f is 3x minus 5. So I have g of 3x minus 5. If you want, you can write it that way. Now, g of this input means this input has to be squared plus 2 times this input minus 1. So now we have 3x minus 5 squared plus 2 times 3x minus 5 minus 1. That's g of f of x. Right? This now is a binomial squared. Heck, we could even use the binomial theorem, but that would be overkill. So I'm just going to I'm going to go a little slowly just to remind us all here. We have 3x minus 5 onto 3x minus 5. I'll do this part here. That's 6x minus 10 minus 1. And here we have 3x times 3x is 9x squared. 3x times negative 5, we could think of it as a negative 5 minus 15x minus another 15x plus 25. There's our plus 6x minus 10 minus 1. What do we have altogether? We have a 9x squared minus 30x plus 6x, so that's minus 24x. We have a 25, 15, 14, plus 14. Okay, that's g of f of x. Very, very different from f of g of x, right? They're not the same at all. They both happen to be trinomials, but that's where the similarities end. Now, what about f of h of x? Well, we're going to put in an input of x into the function h. But when we look up here, remember h is kind of funny. No matter what the input is, the output is always the same, negative 3. So in fact, this output here will be negative 3. So this is the same as f of negative 3. H of x always gives an output of negative 3, no matter what x is. Now, f of negative 3 is what? Well, remind ourselves that f of x is given to us as 3x minus 5. So f of negative 3 means that negative 3 is going to go right here. I'll keep this outer f, I'll write it. I'll keep my brackets for the argument nice and big, and I'll do this computation. I have 3 onto negative 3 minus 5. That gives me f of, this is negative 9 minus 5, that's negative 14. And then f of negative 14, well, that means that now a negative 14 is our input there. So this is going to be 3 onto negative 14 minus 5, which is going to be what? 14 times 3. We've got a 12, we've got a 42, a negative 42 minus 5 is going to be negative 47. So f of h is negative 47. Okay. Now let's take an interesting example here. Let's say f of x is the square root of x, and g of x is x squared plus 3x. Let's first of all determine g of f of x and the domain of this composed function, this composite function. So the input to f is x. Fine, that's easy. So the square root of x is our output. This here has an output of the square root of x. Now we have to think, what values of x are permissible right here? Well, only x is greater than or equal to 0 because you can't square root a negative. So we have a restriction that x must be greater than or equal to 0, imposed right at the beginning. Now, g of square root of x, that says we take the square root of x and we put it here and here. Well, that means that we would have the square root of x squared plus 3 times the square root of x. Fine. What's the square root of x squared? Well, that's actually just x. What is 3 times root x? Well, it's 3 root x. Okay, but we have a restriction on this that x has to be greater than or equal to 0. Okay, so g of f of x is x plus 3 root x, where x is greater than or equal to 0. Now, let's calculate f of g of x and see what that gives us. Well, f of g of x, remember, f of x is root x. I'll put that over on the side. And g of x was what? G of x was x squared plus 3x. F of g of x says, well, first we're going to put in an input of x. X goes into this function. The output is x squared plus 3x. So we now have f of x squared plus 3x. Okay, now are there any restrictions on x at this point? No, there are not. Okay, x for g can be all real numbers. So far here, we don't always write it, but so far we have f of this input for all real numbers x. Now, f of x is the root of x. So this here then is the square root of x squared plus 3x. Now we have a restriction that's a little bit different from the first case. Here, our restriction is that x squared plus 3x has to be greater than or equal to 0, right? Because you can't square root a negative. But this is going to give us a different restriction than we got before. If I'm going to solve this here, I solve by factoring out an x. And then this quadratic, I'll graph. That's one way to do it anyways. Maybe actually I'll do it an easier way first. I'll pretend that this is an equals. I'll solve this. Well, then x equals 0 or negative 3. Those are the two possible numbers that if you plug them in here and here, works out to 0. Because if x is 0, we have 0 times 3, that's 0. If x is negative 3, we have negative 3 times 0, that's 0. Okay, so then we make a number line. We say we have a 0. Well, actually, I got those in the wrong order. We have a negative 3, and we have a 0. And we test each region to see when it makes the left-hand side here greater than or equal to 0, because that's what must be satisfied. So I'll test a number down here. Now I'm going to pick something really small, like negative 10. Negative 10 squared is 100, plus 3 times negative 10, negative 30, that's 70. Is 70 bigger than or equal to 0? It is. So this whole region
all the way down to negative infinity is included as being greater than or equal to 0. And it's a solid dot to include it. Let's test something in between here. I'll pick a negative 1. That's pretty easy. Negative 1 squared is 1, plus 3 times negative 1. That's negative 2. Is negative 2 greater than or equal to 0? No. So this region is rejected. Now I'll test something over here. I'll pick 10 again because that was nice and easy for me. 10 squared is 100, plus 30 times 10 is 30. So we get 130. Is that bigger than or equal to 0? Well, yes, of course it is. So this whole region here, including the 0, is also included. In other words, the values of x that make this true are the ones that show up on this diagram. And as we saw in a recent video, we would write x is in the interval from negative infinity up to negative 3, union 0 to infinity. And as we also saw in that last video, we could switch, we could switch these round brackets around to indicate the same thing. I prefer to use round brackets. Or we could, let's see here. So that's pretty good. Okay, so this now is our domain on this answer. The domain is totally different from the domain that we got for the first one. And it's because the order in which the functions are applied. Okay, now let me just quickly show you how to solve this question right here in another way. If you don't want to go through and guess and check, you can also say, okay, we want this factored quadratic to be greater than or equal to 0. Well, let's imagine that we have y equals this thing. And let's make a little coordinate grid. This is my y and this is my x. And let's plot this parabola. Well, a is 1, so it's a concave up parabola, and up. The vertex, we could use a formula for the vertex, but it doesn't really matter here. We've got these zeros, because it equals 0 when x is negative 3 or 0, and it's concave up. So it's going to look something like this. That's the parabola. That's this y. And this equation says we want y greater than or equal to 0. Where does that happen? Well, that happens here and here. For what x does that happen? These x's and these x's. And so you can see we have the exact same solution as before. Another way to solve this quadratic inequality.
And with that, we have enough to do exercise 2F.
Now remember that equations are not the only ways to show or define relations or functions, right? So we could have set notation here with ordered pairs. We could have graphs. We need to be able to read and understand functions in many different ways. Now, let's suppose here that we were asked to get f of g of 3. Well, we'd go to the g function. We see that the input is a 3, so that takes us here. 3 maps to 2. So this is the same as f of 2. Our output of g of 3 is 2. So now we have an input of 2 for f. F of 2 is 4. So f of g of 3 is 4. Let's go now and suppose we wanted g of f of 3. Well, then we would put in an input of 3 to f. That's here. We get an output of 6. So that's g of 6. And g of 6, we get an output of 3. So that's 3.
Now let's suppose we have two functions with a graph. Let's suppose y1 there is f of x, negative 0.5x plus 1, and y2 there is g of x. Okay, and let's suppose for the moment we're asked to compute g of f of 4. So let's see what this looks like. First of all, we can come into graph. Well, there we are, and we want g of f of 4. So f of 4 is, the blue one is f. It is going to be wherever the 4 is. So it looks like maybe it's a -1. We can go second table on the GDC to find f of 4. It is in fact -1. So f of 4 is -1. So let's just write that down quickly. The f of 4 is -1. We got that from the GDC. So now we're getting g of -1. So g of -1 then, we could actually just look at our table here. We could see that g, the y of -1, is going to be 8. Or if we want to see it on the graph, we could go over to -1 and come up. Yeah, it looks like it's 8. Okay, but the table is actually more clear. I like the table there. G of -1 is 8. And this gives us enough now for exercise 2F. And let's take a look here at a word problem. A life insurance company charges premiums based on age. C, I guess the cost of the premium as a function of N. I guess that would be the, well, it's probably not the age. Let's look at this carefully. C of N is $1.25 times 2004 minus N. Decompose C of N into a composition of two functions. What does each function represent? Well, this looks to me like I have this piece here, and then whatever the answer to that is, I'm timesing it by 1.25. So one of my functions, let's call it g, is taking this whole thing as the input. Let's do that in blue. My input to g is blue, and is going 1.25 times that input. Okay, now what does the blue part look like? That would be our other function, f of, I guess I should use n. F of n is 2024 minus n. What do you think n would actually be? What would the units be for n? See, I think that this is the year of birth. So if we take somebody born, for example, in 2008, then we can get their age. Right? If you subtract 2024, the current year, by 2008, we borrow 1 here, we get 6, we see that this person is 16 years old. If you're born in 2008 and the year is 2024, you're 16. So this function here in blue represents the person's age. So the input here, the domain, is year of birth. And then the output, the range, is their age. And then this green function, well, the input would be the age, and the output would be the premium cost. In other words, somebody who's just 1 year old would cost $1.25, and somebody who's 100 years old would cost $125. Okay, so then my composition, I guess I would say C of n is, which one comes first? Well, first we calculate the age, and then that's the input to g. So g of f of n. There we are. And we now have enough to do exercise 2H.